for joining us. This is our 51 meeting. Super excited to have that. And we have a special guest today. I'll introduce him in a second. You all know him. Uh, so we'll go through the regular few seconds of our welcome slides, just welcoming new members. If you are a new member, I'll briefly speak about what we do here. And the main course of today, obviously, Deane is our guest, and I'm super happy to have him here speaking on functional programming and similar. So we'll get it in a minute. If you are new, welcome. I'm very happy to have you. We speak about C++, all kinds of ideas, all kinds of domains within C++. We have all the recording uploaded and also the slides. So if you need anything, you can find it. Just ping me either through Discord, or if you're in Qualcomm, you can ping me internally. If you would like to present anything, any length, any topic, please feel free to do that. We have few things lined up for the next few meetups, so that's I'm super excited to have that. It is sponsored by my VP, Charles, which is the wireless R&D software in Qualcomm. So thank you, Charles, for sponsoring that. Uploading the talks, the slides, and also the YouTube channel is populated with that, with the recording. If you need to the Discord link, let me know. I'll provide it to you. SDCPP Meetup YouTube channel is our channel. I have a handle, SDCPP Meetup. My handle is Kobe_CA. I sometime write into I'm writing some blog posts in Martin's Volbert blog, and I had a few days ago actually finally submitted a coroutine blog post that is related to the Jan meetup a few months back. I promised to have that and finally did that. I always want to make it a short coroutine related domain, related topic, but it's always a kind of a huge topic to begin with. But hopefully you can enjoy it. So it's in Martin's blog. You can visit that later. I'll let Ben introduce the actual abstract. I want to introduce Ben himself. So Ben Deane, he's a principal software engineer at Intel. So Ben has been programming in C++ for this whole millennium. He spent just over 20 years in the games industry, working for companies like EA and Blizzard, which is, if you're a gamer, and I used to be a gamer, very respectable companies, obviously. Many of the games he worked on used to be fondly remembered, but now he's accepted that they are probably mostly forgotten. And I was very curious to hear what kind of games you were working on, just as an anecdote. After getting more interested in modern C++, he started giving internal company talks, and then talks at various conferences, spreading ideas about types, algorithms, and declarative and functional techniques. In 2018, he left the games industry and worked in finance for a short spell, writing high-frequency trading platform using the most modern C++ that compilers could support. And today he's a principal software engineer at Intel, where he puts monads inside your CPUs, which is very interesting. Welcome, Ben. Happy to have you.
Thank you. Thanks for having me. Thanks for inviting me. Yeah, there were a few, sort of jokes in that bio. Let me share my screen then, I suppose, and we can get started. Let's see. Yes, that should be the correct screen. You should all now be seeing the title slide. Yes?
Yeah.
Cool. Okay, well, yes, thanks for the introduction, Kobe. This talk, I just gave this talk in Aspen at C++ Now last month, about a month ago now, a little over a month ago. The talk slot there is 90 minutes, so this is quite a long talk, but since you know, the meetup is scheduled for an hour. I'm going to try and maybe skip a couple of sections, but please do ask questions as we go, and I'll answer them. I probably won't be able to see who's talking because I'm looking at the speaker view here and I don't see anyone talking, but please interrupt me, ask questions as we go. All the code you're going to see has compiled at some point in its lifetime. And I hope that by the end of this talk, some of you will look at your code with fresh eyes. So it's all about applicative or applicative functor, which is, in my view, a forgotten functional pattern. We hear a lot about monads. We hear a lot about functors, meaning the functional pattern. But applicative functor is this functional pattern which, as we'll see, fits somewhere in between those two, and it's super useful. You know, we hear a lot about monads, monadic this, monadic that. My thesis for this talk is that applicative is a lot more useful than monad, a little bit simpler, and often it's all you need. Anyway, let's start by an introduction or a refresher for some of you, I'm sure, about functor and monad and see where applicative fits. First, I had a quick survey among folks. So you might be able to answer yes to one or more of these sort of points. Several people have heard of these things, kind of understand how they work. Maybe you don't see many use cases in your code, or maybe you've written code that was good. Maybe you completely feel au fait with them and understand them. And maybe this last point even. Or maybe you've had this experience. I've had this experience sometimes. So don't worry too much about what a functional pattern is. The point of patterns is what they do. So we'll think about what these things do rather than thinking about kind of getting a handle on some notion of what they are. That's a bit less important, I think. Anyway, we have several examples of functors in C++. And broadly, a functor is a class template which has one argument. And some good examples we have are optional. We have vector, ranges in general are functors. We have expected in C++ 23. That takes two arguments, but if we consider that the error type is bound, so if we bind the error type, then the value type in expected remains free, and then it's a functor. And the characteristic function on a functor is fmap, right? And in C++, fmap looks like this. Very general. It's worth noting that the particular implementation of fmap is different for every functor. So it's going to be a different implementation for optional than for vector than for expected. But very generally, fmap takes a function and it takes a value, a functorial value, and it unwraps that value in some way. So in the case of optional, it's if there's a value in the optional, if the optional is engaged, and it will run the function on that, and then wrap it back up in a functor. Okay, so that's fmap. And in Haskell, so in C++ it looks like that, which is a lot of syntax. In Haskell it looks like this. And for this reason, I'll be using Haskell type signatures. I won't be using any much Haskell in this talk, but the type signatures are much, once you get used to reading them, much easier than C++. So what this is saying is fmap takes everything. Every argument is separated by an arrow, right? And the last argument you can think of after the last arrow, that's what the function returns, and everything before that are the arguments. So fmap takes a function from A's to B in this case. So A arrow B is a function type, and that's the first argument to fmap. Second argument to fmap is the functorial value, which we saw before, and it returns a B inside a functor. Right, so that's saying exactly what this C++ is saying, except in one line. So hopefully that much is enough to, and for those of you who weren't used to these type signatures before, that's enough to get you going. So yeah, here's how you read Haskell type signatures. Double colon means has type, and we can see the three args, or arg1, arg2, and the return type. And then when you have the equivalent of a template in C++, you don't have the angle brackets. So you just have FA for the A inside the functor, or F of A to B, right? So F is like our class template, and then the A or the A to B is like the value inside there. Everyone good with functors? I'll assume silence means yes.
Yes, yes.
Yes. Okay, cool. So that was functors. So monads are in C++, the things that are functors tend to be monads as well. So again, it's also a class template of one argument, same familiar examples, optional, vector, expected. At this time, the characteristic function is bind, or there are a couple of ways to express it. We usually say bind, join is another way. Now fmap looked, the way it did. Bind looks similar. The difference here is that this time the function we pass to bind returns a functorial value. So if you think of this concretely in terms of optional, it would be a function would be returning an optional, and we'd have an optional A, and we get back the same type of optional as the function returns, right? And in Haskell, bind looks like this is spelled with this funny operator. But you can see in type signature, it takes two arguments. First argument is A inside a monadic A. Second argument is a function from A's that returns monadic B's, and bind returns a monadic B. Okay, so a few sort of equivalences you can see here. I mentioned join. So if you think about what happens when you try to fmap a function that returns a functorial value, say you have a function returning an optional, and you fmap that into an optional, then what you get is an optional, right? An optional inside an optional. So the value will be double wrapped. And join is a function that collapses that wrapping to a single wrapping, right? You can see the type of join there. It takes an option, it takes a monad of A and collapses it down to monad of A. And so fmap followed by join is the same thing as bind. That's just what this slide is saying. We can see that we can see the comparison here. So fmap takes the function that just returns regular B's. That's the top line, and then functorial A to functorial B. And if you look 2 lines down, bind, and I've just flipped the arguments around, but it's equivalent. You can see how they line up. This time the function is returning a monadic B, and then monad of A to monad of B. Okay, so that's where fmap and bind are. And then we have some, like I said, we have monadic functions for stood optional in the standard as of, I think, C++ 23. So for instance, we have transform. This is a member function on stood optional, and you pass it a function, and it's fmap basically. It runs that function on the value inside the optional, gives you back a new optional, right? So that's transform. That's in C++ 23, and we have and then, right? The same signature, right? From the look of it, also takes a function. This time, we note that it says the return type must be a specialization of stood optional, right? So this is bind. This is, you have a function that returns an optional, you use and then. You have a function that returns a regular value, you use transform. So we have transform is fmap, and then is bind. Okay, so much. That's all. Hopefully, review or familiar to folks somewhat. So applicative has an interesting history. If we go back in the day in Haskell, in the mid 90s, Haskell has type classes, which are very similar to C++ concepts. And it has these 2 type classes. It has functor and monad. And in some sense, monad derives from functor. So every monad is a functor. And there's the IO monad and the list monad and the maybe monad. They're the familiar monads in Haskell at the time. And then around about the mid 2000s, in particular in a paper in 2008, applicative appears as this sort of new pattern. It's related to both of them. It's also the case that applicative is short for applicative functor. So every applicative is a functor, right? And so applicative also derives from functor, but applicative and monad at this time don't have any shared heritage, right? Even though they really do. And so in 2014, GHC 7.0, 7.10 made this change. So interposing applicative between functor and monad. So this is where applicative fits. So every monad is an applicative, and every applicative is a functor. Okay. So in C++, optional is all three of these things, and vector is all three of these things. And we have monadic functions, and indeed we have fmap, the characteristic function on functor or transform, and we have and then, which is bind, which is characteristic on monad. But we're missing the middle slice of this cake, if you like. Okay, that's the end of review. So let's take a look at what applicative might look like in C++ and the mechanics of it. So there are a few talks out there. In particular, there's a talk by David Sankel about all three of these patterns, and by Mikhail Dominiak. In that talk, actually, the title doesn't include applicative, and he says he won't talk about applicative, but about halfway through the talk, he does briefly cover it. He says, I told you I wasn't going to say this, but I will. And David Sankel repeated that talk in 2020. And basically, these talks say the same thing. And most work you'll see introducing applicative, including most work in books and on YouTube videos, says the same thing. So, we know what fmap looks like. We know what bind looks like. So here we introduce this other characteristic function on applicative, which is the third line here. It's called, I tend to call it app, because apply has flashes of std apply. So I tend to call it app. And it looks like this. So it's for when you have a function, like an optional function, and you want to apply that to an optional int, right? And get out an optional string or whatever it is. And, so this is how the existing work presents it. And then, they explain this type signature. And as a C++ programmer, you probably go away thinking, well, that's fine, but when am I ever going to have a function inside an optional? This isn't a use case that really I use a lot. So applicative kind of falls flat. And they invariably says the footnote, this can be used to apply functions in more than one argument. Well, that's the whole point, right? That to my thinking that they're burying the lead a bit there. The whole point of applicative is to apply functions of more than one argument, which is kind of important. And what it does is it generalizes fmap. So if we think about how we would write fmap for more than a one argument function, right? The fmap that we know is fmap1 on this slide, right? That's the you've got a function, you've got an optional int, you want an optional string, your function is toString or something. fmap2, we've got a function of two arguments there, and therefore we've got two optionals to apply it to, and it gives us back the fc there. Likewise, fmap3. And if we go back the other way to fmap0, then we have no function and just a value, and we're lifting it into the functor. Anyway, so fmap0 is called pure, and app, or this angle star operator, is written this way in Haskell, and this is what all the literature says. It applies a function inside the functor, and in Haskell it has this kind of signature which in C++ doesn't seem very useful to us because of the way Haskell works. Because Haskell has built-in partial application and built-in curried functions, and all functions in Haskell are unary functions. There are no n-argument functions. There are just one-argument functions that might themselves return the function. And so this formulation of applicative is good for Haskell, but it kind of falls flat for C++. So in Haskell, it looks like this. Plus is a binary operator. It takes two ints and returns an int, let's say. And in Haskell, maybe is what they call optional, and just is, the constructor for maybe. So if we fmap plus onto just one, what we get is that function in a functor, right? The +1 function, the maybe +1 function. And then we can use apply to take that function in a functor and apply it to just 2, and then we get the expected. We get maybe 3, right? So it's all very straightforward in Haskell, and you know, there's a very nice symmetry between what it looks like in sort of regular int land. So obviously we do +1, 2, and then inside, you know, the maybe functor, we do pure plus applied to just 1, applied to just 2, right? So there's kind of this symmetric formulation, if you like. Now, if we look in C++, we have tons of, well, quite a few papers, right, in recent years that talk about, let's add functional patterns. Let's add functor, let's add monadic. You know, we have that for expected and optional now. We have, but all of these papers say almost nothing about applicative, right? If they do say anything, they say things like Cy Brand said. They said, I couldn't think of many use cases of this in C++. And from all of the other papers that might be expected to have functional patterns in, many of them don't have any mention of applicative. And I think it's because this strange formulation doesn't really work well in C++. So, okay, so much for Haskell. Let's have a look at C++. Now, there's a particular paper, P2561, where Barry Revson explores a problem, right? And the problem is sort of exactly the problem that is you want a multi-argument fmap for, right? So you have two functions, right? And they return monadic values. In this case, in the paper, it stood expected. And you want to apply a function, in this case, strucat, to those two values, right? And so you end up having to write something like this. You know, you call the first one, and then you have to test it. And if it's not there, your outer function has to return the unexpected, and the same thing with the second one. And only if they're both there do you finally get to actually do what you wanted to do and return the result in expected. So this is the very simple kind of code that P2561 presents, and there's a couple of ways to solve this that the paper explores. Manual error propagation, like we just saw, is one of them. Some libraries like Boost Outcome give macros. You can get quote unquote nice syntax with using exceptions or coroutines, but you know, either or both of those might not be usable for a particular use case in C++. And the paper concludes that the best case today involves macros. Well, you know, Cy wrote this. Cy wrote this in their paper from 0798 from the stood optional monadic values, monadic operations. This is the use case, right? So let's try and answer this question. Let's try and write this code here with a nicer syntax using functional patterns. So our goals are just to be, I don't want any macros. I don't want manual control flow. And I want this kind of just natural looking, good looking code that is also efficient. Before I tackle it with expected, I want to tackle it with optional. Now, the first observation to make is that we can solve this problem with the monadic API that we have on optional, right? And this solves it, right? So we're chaining the optionals together. We're saying we're using and then, which is bind, right? And like I said earlier, every monad is a applicative, so you can use the monad stuff to solve these kind of applicative problems. But you know, how did that do? Well, I don't think it did very well. This is not declarative, right? Monadic stuff is pretty imperative. We've got manual-ish control flow with all this nesting. Good looking code? No, not to my mind. So let's try and solve the problem. So let's start firstly by implementing partial application. Happily, I don't have to implement it because it's already implemented by my local folks at my local meetup. We did this sometime last year. So let's just take a brief look at this function. It's called curry. It's going to return the result of applying f to the args, but there might not be enough args to fully apply the function, right? If there are enough args to apply it, it's going to just apply it and return the result. That's the first return there. Otherwise, it's going to capture those args inside a lambda along with the function. And when that lambda gets called with some more args, it's going to return the result of curry, right? Which is going to be recursive, which, again, if there's enough args to the lambda at that point, if enough args have been accumulated, then curry will trigger the first return. So this is partial application, right, in C++. Yeah, and like I say, we did that in the Denver meetup. I don't have to tell you folks to find a meetup online. Okay, so given that, here's what fmap looks like for optional. We are going to, if there's a value inside the optional we're given, then we're going to return the result of currying f with it, which might be the full application of f, but might not be, right? So each optional we get passed, we're going to curry that in, as it were, partially apply. And here's app, the characteristic function on applicative. So the only difference here is that where fmap takes an f, app takes an optional function, right? Remember, it takes a function inside the functor, as it were. But otherwise, it's going to do pretty much the same thing. Now, if they're both engaged, then we unwrap them both and curry them, right? So what does the code look like if we have that? Well, here we have our code from before. It's using optional, not expected this time. It looks okay. It doesn't look great. It's okay. So how did we do? Well, there are no macros. There's no manual control flow. It's fairly declarative. Good looking code, not the greatest yet, and efficient, not well. We're calling foo and bar, right? We're not earlying out if foo failed. So that's interesting. Okay, so yeah, it was okay. We had to wrap std format in the lambda because you can't in general take the address of a standard library function. You have to do that kind of thing. The last line there is a little awkward. If I go back to that return app of fmap lf, b, it's a little awkward for my taste. But we can say that's slightly better. But C++ isn't Haskell, right? We can have functions of more than one argument in a sense. Now, yes, functions of more than one argument are exactly equivalent to functions of one argument, and currying. So why don't we try a different take? Why don't we have fmap take a variadic pack of arguments? So, and this is what it looks like. It's exactly the same as fmap from before, except that we've turned the single optional into a pack of optionals. So the check just checks that all of the optionals are engaged in a fold expression there, and we invoke, and we don't need curry now, right? Because we don't need to partially apply. We're giving the arguments in the pack. We don't have fmap taking the one argument anymore. Note that this is not the same as optional transform, because optional transform is a member function. This has to be a free function because it takes multiple optionals, right? But let's see what that looks like. Well, I think a little better yet, right? We've got rid of app. We've just given fmap multiple arguments. So slightly better than before. I would put a heart in the good looking code column now. Now, efficiency, we still have the thing of like, if foo fails, we don't early out, right? We still call bar. So we're still doing more work perhaps than we need to. Now, in some cases, it might be fine, but let's see what we can do. Yeah, so exactly what I just said. This is the efficiency. So let's try and figure out a solution to this. Now, Haskell gets a free pass here because it's lazy by default. C++ is not, of course, lazy by default. In order to be declarative here, we will need to evaluate function arguments lazily. In order to do that, we want our code to look something like this, I think. Or this is about the best we can do in C++, right? So we want to say return fmap of L, which is the format function wrapped in the lambda, right? Remember? And we want a lazy call of foo with I and a lazy call of bar with I. So what's lazy call? Well, it's a function that returns a lazy object, right? There is, and the lazy object wraps its arguments in a lambda. And so here it is. It's wrapping its arguments in a lambda, and it's producing the result lazily, so which is the invoke result t here. When we test it in that fold expression, that's when it's going to call the function and say, did it pass or fail, right? It's going to hold on to the value. And then when we dereference it, right, for calling the outer function, that's when it's going to yield its value that they've produced, right? So it's just a kind of way of lazily applying the function and buffering the result. And then the code looks like this. So, you might have your own take on whether this is better. In some cases, you can take your pick. You can use lazy evaluation, or just use the eager function evaluation if you're not worried. It really depends on your use cases, Now, the question some of you may be asking is, this was a bunch of programming. Did the optimizer see through it all? In my experiments, yes, it did. Like it's real easy for the optimizer to see through tiny lambdas which are used only in one function like this. And at least in micro benchmarks, the compiler, the optimizer does do the right thing. So how do we do now? Well, I think we did pretty well. This is, I think I'd be happy to have this in my code. That was with optional. So let's see what it looks like with expected. So this time, same as before, except instead of stood optional, we have stood expected, right? So in this case, foo and bar themselves return expected ints instead of optional ints. Can we make it work the same way? And of course, the answer is yes. There's a little more to be done. This is what fmap looks like for expected, right? We need to do a bit of metaprogramming to pull some types out. So T is going to be the result of invoking f on the values. That's fine. That's clear. That's kind of what we had before. E is going to be the error type, and the simplest way I could do this for slideware was to use common type. Okay, so the things coming in here, the texps, those are actually going to be lazy things. They aren't going to be actual stood expected. They're going to be lazy things. But the lazy thing is going to have all the machinery we want. So in particular, it's going to expose an error T. And given the type and the error, we know how to make the return type of this function. It's going to be an expected of that type and error. And then the code's going to look very much like it did for optional. We're going to test if all the lazy expected values are engaged. And if they are, we're going to call the function and return. Otherwise, we'll return an error. So, okay, so let's have a look at what the success case looks like. Here's part of our lazy that does the success case, right? So this time, very similar to optional, it's exposing the error type, as I said. But the bool test again is going to actually call the function and buffer the value, and then the dereference is going to return that value, assuming it was a success, right? So the failure case, how do we recover the error? Well, we actually need short circuiting. We used an and fold expression to enumerate all the values, which means we already got short circuiting there. So the sort of natural counterpart to that is to use an or fold to get the expression. So I use this little trick where I just wrap them in an invert type. So, and the invert type is going to evaluate with a Boolean with the bool conversion to true when the original function failed. So when it doesn't have a value, right? The inversion is going to be true this time. And then to get the error, we just get the error out of the expected value that is buffered. So that's the plan. And then the code that exercises that does the or fold expression you can see near the bottom there. We are inverting all of the t's and calling this little extract error lambda because we need to like extract the error but return a bool for the or to work. So that's just what that's doing. And then we were going to return the unexpected value. And we know this is safe. We know if we get here that one of the functions failed, returned an unexpected value, and we know that that's the one that we're going to recover, right? So that's what it looks like. And then the call site looks exactly the same as it did for optional. Same call site structure, and in this case, foo and bar return expected values, and we return an expected value. So does the optimizer still see through all this? And again, in my experiments, yes. Now, okay, the conclusion here. Well, the original paper is talking about an error propagation operator, so maybe there's still room for that in the language. C++ is full of things in the library that could arguably be in the language. But when we have this conversation, I think we need to be aware of what applicative does, because this is precisely what it does. It generalizes fmap to multiple arguments. And in my opinion, the best use case today does not involve macros. Okay, I just want to pause at this point and take any questions, because I've shown a lot of code. We're moving quite fast. Hopefully everyone followed, the argument in the paper and the way we could solve it with this variadic fmap, which I'm saying is the same thing as applicative. So are there any questions at this point?
I have a basic one, actually, from the early part of the slides. You mentioned ranges and vector as monadic. Is this true?
Yes. We don't have any monadic operations for them yet in C++, but a vector is a monad. Yes, a range is a monad. Later in the talk, I'll come to explaining how exactly.
Okay, thanks. Okay, so I'm saying, the way applicative gets normally explained is for a function in a functor, right? And I'm saying a variadic fmap is equivalent. So am I to be believed? Is this really equivalent? Well, we can see that it's equivalent because we can show how to implement app in terms of variadic fmap. And if we can do that, then we know that it's just as powerful, right? Well, here it is. Here is app. It takes an optional function and an optional value. This is for optional, right? And what we're going to do is call variadic fmap, right? What are we going to call it with? Well, the first argument, the function that we are fmapping is invoke, right? It's only wrapped in a lambda because, again, you're not allowed to pass std invoke because it's a library function. But the first argument to fmap is going to be invoke. And what's it going to be fmapped over? Well, it's going to be fmapped over the function in the optional and the value in the optional. So it's going to end up calling invoke of f on value. That's what we want, right? So it's that simple. This is app implemented in terms of variadic fmap in C++. And then in Haskell, it's called, in Haskell, they don't have variadics, right? So that's where C++ really wins. But they have occasionally things like lift A2 is exactly what we showed earlier as fmap with 2 arguments, right? They don't have fmap with n arguments like we can write it. But exactly the same thing. If you, and they spell invoke $, right? So if in Haskell, if you lift A2 of $, what you get is app.
right? The first line in the Haskell and the last type signature in the Haskell, they're exactly the same. Okay, so I've motivated a bit what applicative is and where it fits, but I've also said every monad is an applicative. So what's the real difference here? When would you use one? When would you use the other? Now, is it a question of power? So every monad is an applicative, and in some sense, monad is more powerful than applicative. You can do everything with monad that you can do with applicative. We saw in the paper, in the question in the paper, like it can be solved with and then. I showed that piece of code. It was horrible and ugly, but it can be solved. So if monad's more powerful than applicative, what does that mean? Well, more power means more constraints, right? Here's the code that we saw. Everything applicative can do, monad can do, but not better. So, besides the syntax, what's the actual difference here? A monad is for when you need to make runtime choices based on what came before, right? So if we look in the nested calls here, the call inside foo's and then, we could have an if statement in here somewhere saying, depending on what the value of f is, we choose what to do, right? Or depending on what the value of b is, we choose what to do. That's what monad is for, when you need to make choices at runtime based on what came before. In other words, when you have data dependencies. In other words, you are inherently serial, right? There's a serial nature to the computation. It's not parallel at all. Now, applicative, on the other hand, is inherently parallel, right? Now, what I showed was a fold expression, and fold expressions have short circuiting, and that happens to be serial, right? And I showed that just for slideware, but that's just an engineering choice, right? If I had something where it was very cheap to evaluate all these optionals in parallel, no reason I couldn't do that, right? Doesn't matter if I evaluate them all. As long as if they all succeed, then I know that I'm going to return success. If any of them fail, I'm not, right? This is purely an engineering choice at this point. Like applicative itself, the pattern doesn't require me to short circuit. So that's the key difference, right? So we would use a monad when we need that dependency, when we have that serial operation, we have that data dependency. If we don't have data dependency, well, applicative is a sort of less powerful and therefore more flexible thing. And this is how functional programmers kind of think about architecture. They think in terms of, well, do I have a data dependency? Well, that probably means I need a monad. Or, do I want parallelism? That means I can do applicative. Okay. And that's how I've heard functional programmers thinking about architecture. And that's the real difference in monad and applicative functor. So there was a question a minute ago about vectors, ranges, sequences in general. Let's see about how they're applicative, how they're functors, how they're monads. Okay. So a range, I have claimed, is a monad, which means it's an applicative and means it's a functor. So how would it be a functor? Well, the characteristic function fmap is implemented by transform. When we transform a range, we're giving it a function to apply pointwise to every value in that range. And that is what fmap means for a sequence. So StudView's transform here is doing the same job as fmap. Conceptually, it is fmap, right? A range is also a monad. So what's the characteristic function on monad? It's bind. And we know that bind takes a function that returns a monadic value. So in this case, we'll have a function that returns a range. So here's an example of a range being a monad. If we're playing a game of chess or whatever, we have a board position and we want to enumerate the next board positions. Well, that's going to be the possible next board positions is going to be a range of boards which are reachable from this board, right? And then if we want to min-max that algorithm and go down to a certain depth, each one of those boards in that range is going to itself produce a range of next possible moves. How are we going to collapse all those down? We're going to use bind, which we don't have the monadic function in C++, but like I showed earlier, bind is equivalent to fmap followed by join. So we call fmap transform, and we do have join, right? So if we take a range of boards, in this case, it's just one board, just a single, we can transform that range by running next positions. That's going to get us a range of ranges, and then we'll join those together to get back to a single range. That transform followed by join is monadic bind. It's the same operation. Okay, so we have fmap in the form of transform. We have bind, transform followed by join. How is range an applicative then? How would we write app? So what we need here is either the function inside the functor formulation, which is to say we have a range of functions and we want to apply them to a range of values, right? You can think of it that way. That's the traditional way. Or in variadic fmap form, we have a function of n arguments and n ranges, right? We're generalizing fmap, right? So we have a function in the standard whose type signature looks like this, and it's called zip transform. And it takes a function of n arguments and the n ranges, and it zips them all together, right? This is one formulation of applicative on ranges, and it's in the standard, right? Now the question we have to ask is, like, there's not just one. Sometimes for a data structure, there's not just one formulation of applicative. So we have to, we can see that this is a formulation, but we have to ask, does this lead us to a monad? Like, is this formulation of applicative also a monad, right? Remember, every monad's an applicative, but not necessarily the other way around. We have to check that. So let's check that. We know that zip transform view is, I'm saying sort of loose language, is the characteristic applicative function on ranges. Is the structure resulting from that also a monad? Well, let's go through the types, right? Let's say we have two functions and they return ranges, and then zipping them together gives us f1 applied to a, right? Which gives us, in this case, might give us a sequence of three things, and f2 applied to b gives. Yeah, I'm sorry about the a's, b's, and c's here, but basically, we're zipping the functions with the list pointwise. So f1's applied to a and f2's applied to b. Now we have to consider they might return sublists of different lengths, subsequences of different lengths. How would we call join on that, right? Because if this is a monad, we need to know how to collapse this down to a single list again. Well, one way, in fact, the only way that really works here is to take the ith element from the ith list. But the problem with this is that the ith list might not contain an ith element, right? So this is not a monad. It is applicative. Zip transform view gives us an applicative instance on sequences, but that doesn't translate into being a monad as well. However, we have another function that almost has this same signature. This is variadic fmap again, function of n arguments and n ranges. And that function is Cartesian product, right? And you might say, well, it doesn't take a function, right? The implicit function that it's doing inside is make tuple, right? So Cartesian product view looks like this. It takes a bunch of range, a variadic pack of ranges, and it produces a range of tuples, and each tuple represents one element of the Cartesian product of the ranges. And given this, we could f map the real function we want to run over this by applying it to the tuple with stood apply, right? So Cartesian product view is an applicative functor. The question is, again, is it also a monad? And the answer this time is yes, right? Because if we run Cartesian product over two ranges, what we can do is take those tuples, like turn them, or rather, you know, because we haven't actually passed in the real function we want to run, it ran make tuple. But if we actually apply the real function over that to give us then lists, right? So f here is a function that returns, sorry, when I say list, I mean sequence or range. F is a function that returns a range, right? So it returns a monadic value. So now we've got a range of ranges, and this time we can just join them together and we get something that behaves properly as a monad. So it obeys all the monad laws, which pretty much means it's associative, right? Which is the law that zip lists ran afoul of. So zip transform view is not a monad, does not give rise to a monad, but Cartesian product view does. They're both possible formulations of applicative functor on sequences, but one of them is a monad also, one of them is not. Now, if you have been paying attention, you may note that applicative on ranges is list comprehensions, right? So we sort of have list comprehensions that really look horrible compared to other languages, but they are equivalent. You know, in Python, it looks like the first example. In Haskell, it looks like the second example. So we've got, you know, two lists, and what you get back is the Cartesian product over those lists with the appropriate function applied. And in C++, we can run the Cartesian product and then run the function over that, and what we get back is the same thing, right? So other languages have list comprehensions. We have to do a little bit more work, but it's exactly equivalent. Okay. Any questions at this point? That's the end of the section about ranges.
So I have a question. If you can go back to, I'm just trying to grok one line. Go 776, I think.
Okay.
Yeah. Yeah, this one. So I'm trying
Mhm.
to grok the. So this is a function. So the auto next positions. It returns ranges range.
Oh, yeah. It's what's the return type there is a concept.
Oh,
That's a concept constraint on the
okay.
return type, which
Okay.
may be unfamiliar to some folks. Yes.
Yeah.
So I'm
I
saying
missed the
that it
concept.
returns something that fulfills the range concept.
Yes. Thank you. Completely forgot about it.
Yeah, C++ is moving fast. I mean, it took me a while to get used to that kind of thing also.
Yeah.
Okay. Yes, where are we? Okay, so we saw Cartesian product on lists. Real quickly, this is going to be, you know, critting you with a wall of C++ a bit. We can do Cartesian product on heterogeneous sequences, right? So ranges are homogeneous sequences of one type, but we also have the tuple, which is a sequence of heterogeneous types. So could we make Cartesian product for that? Well, what would it look like? Here's two tuples. If we take the Cartesian product of them, we get a tuple of tuples, which each subtuple represents one element of the Cartesian product, right? This is what it looks like. A couple of more concrete examples. If we take the Cartesian product of the tuples 1, 2 and the tuple 3, 4, then we get the tuple of that. If we have a Cartesian product of one tuple, what we get is elements inside tuples in the outer tuple. And if we take Cartesian product of an empty tuple, therefore, what we get is a tuple containing an empty tuple, right? This is how it breaks down if you sort of think about it recursively. And given this, we can sketch a recursive algorithm. So what we're going to do is we're going to split the tuples that we're given into sort of head and tail. We're going to do a classic recursive algorithm. So we're going to say, give me the Cartesian product of the tails. Okay. And so for each element in the first tuple, I'm going to take each element of it and prepend it to each of the Cartesian product of the tails. So, and if there are no tuples left, I'm going to return just the what we saw before, the empty tuple. Where are we? Here. So, okay, so we're going to be given a bunch of tuples. We're going to say one of them's the first tuple, and then there's the rest. We're going to just do the Cartesian product of the rest, and then we're going to take that first tuple, and we're going to take each element from it and prepend it to each thing in the remaining Cartesian product. Okay, everyone clear on the algorithm? And it looks like this, which is which you know you can look at and sort of understand on your own time. I don't have time to, but I will draw attention to a couple of things. So you can see that the base case is there, right? So if there are no tuples, we're going to return the tuple containing one empty tuple. Otherwise, we have the recursive step. So you can see that with the recursive step, you can see we're doing the Cartesian product of the rest. That's C. And then we're going to take the first tuple and get its head and prepend it to everything in the Cartesian product, right? That's exactly. So, by the way, if you're wondering about that stood make tuple, I wonder how many of you have run into this. Do you know what this returns? In this case, I would like it to return a tuple of an empty tuple, but
Yes.
actually it returns, yeah, someone's saying yes, maybe they've been bitten by this as well. I've been bitten by this twice. It returns an empty tuple because it's triggering the copy constructor of tuple, right? So yeah, CTAD, someone on the committee told me that this came up in standardizing class template argument deduction. They decided to go this way. It's kind of annoying in generic code. Anyway, right? This formulation we saw here sort of suffers from the same thing as Cartesian product on ranges, which is that the function it's using is baked in. It's using make tuple in the middle there. But we don't have that. We don't have to do that. We can actually give it a real function. And in this recursive solution, the way the tuples are the way the elements are going to be built up by applying the real function instead of make tuple is going to be as if by partial application applying arguments in reverse. So the way it works out if you think about the recursion. Helpfully, we already have curry from earlier on, and we can turn it into a reversing curry, so a curry that flips its arguments. This is exactly the same as curry you saw before, except that in the nested return, where we call flip curry in the recursive here, we flip around the order of A's and args, so we expand to A's first. So we're building arguments, applying them from the end rather than from the first argument. But otherwise, that's just like we saw before. And now we can take our Cartesian product from before and pass it an f, a function to actually apply instead of make tuple. It's still returning a tuple, so we will still have make tuple in there for the outer tuple. But the base case now is making a tuple containing the curried function with no arguments yet, right? And then as we unwind the recursion, each time we're going to apply another argument, building it up in reverse until eventually we get to eventually the call, the most deeply nested call here, make tuple of subs. Subs are those partially applied functions, and eventually they will be fully applied when we apply the sort of last or first argument, as it will be. And that's, here's the original one again. Here's the one with f passed in. So you can see the structure of them is very, very similar. It's just that we've generalized it. Instead of calling make tuple, we're able to pass a function in. Cool. Well, that was just a bit of fun. I don't want to spend too much time on it because we are time bound, but we're getting through the material here. So I just wanted to talk about a few more examples of applicatives because they really are everywhere. Parsing and asynchronous execution are two great examples. Parsing is one of the original use cases for applicative. If you've seen Jason and my talk about context for all the things, in that talk I said a parser for things is a function from strings to list of pairs of things and strings. And what I mean by that is that when you're parsing a string, what you're getting out here is the t. You're parsing a string view. Now there might be several ways to parse it, and that's what the range represents. Oftentimes we might just say there's only one way to parse, so you can either pass or fail. So it will be optional, which is just like a range of at most one thing, right? But in general, it's a range of pairs, and the pair is the thing that you parsed out, the t, together with the remaining text. And in context for all the things, I presented this function, which combines two parsers. So it calls parser 1, and then it calls parser 2. And given the two things that are parsed out, it applies the function to them. And it's a combinator, so what you get out is a parser FC. And based on what we saw earlier, this looks kind of familiar. This is f map of two arguments, right? Just that the function is the third argument instead of the first one. But if we flip the arguments around so the function comes first, we've got a function from A to B to C, and then parser of A, parser of B, parser of C. It's exactly f map 2. And I used it in that talk mostly in two different flavors. So I overloaded less than and greater than, just to mean run the first parser, then run the second parser, and only keep the thing that's on the greater than side, right? So one of the parsers, I need to run it on the text, but I don't care to keep what it produces. So I can write things like this. I can write a thing that parses quotes and a thing that parses strings. And the thing that parses strings is just parsing a bunch of characters that aren't quotes, right? And then I can use my angle bracket overloads, which are, running that combined, which is really applicative. Throwing away the quotes, I don't need to know that a string was surrounded by quotes. I already know that. And it makes a very declarative code. And of course, I didn't make up the technique for the talk. I got it straight out of Haskell. Where they have these two operators, which do basically the same thing. In this case, they keep the thing that the arrow points to, because Haskell has generalized operators. Like we don't get to make up our own syntax for operators in C++. So I had to go with less than and greater than, and I keep the larger thing. So let's take a look at monadic parsing versus applicative parsing. Remember I said that monads are for when you have data dependencies, and applicative when you don't is better. Now, my apologies, this is the only real bit of actual Haskell in the talk. Haskell, of course, is a functional language, a purely functional language. The funny thing is that when you use monads, it looks very procedural, because this do statement, this do block, is running these things in order. So we're parsing a 2-digit hex number like OXAB. We're going to parse the OX, and then we're going to parse the first hex digit and call it high nibble, and then parse the next hex digit and call it low nibble, and then apply the hexify function to both of those. And that's that. Return here is not the same as return in C++, but it doesn't matter. Anyway, it's a procedural function. And as you can imagine, this looks horrible in C++. Like we saw earlier, the monadic way to solve the foo bar and the strucat, they're still nested. C++ doesn't have this do syntax, so you'd be nested like 4, 5, 6 times here in C++. When you use applicative, it really turns much more declarative, right? So what's this saying? Well, before we were parsing out things and then calling hexify. Now we're saying we're going to take the hexify function and we're going to fmap it. That dollar angle bracket thing is the same as fmap. We're going to fmap into one parser. The first parser here is composed by parsing out the OX and parsing out the hex digit and only keeping the hex digit, right? So that's a formulation of app, that star angle in the middle there. And then, that's that produces one argument to hexify, and the other argument is the next hex digit, right? So we're going to use app to apply that, and that's much more declarative. So in C++, this would look, syntax aside, but it would look it would be declarative in the same way. It wouldn't be procedural, right? Because we'd be able to say almost exactly the same. We're basically saying fmap hexify into the result of parsing hex digit twice. And the first instance of parsing hex digit is self-composed with parsing the OX. So again, applicative, when you're parsing things, almost always applicative is all you need. There's I have to put a caveat in because this is C++, and C++ is of course not parsed by applicative. You need much more than that. But if you have a context-free grammar, if you have a sort of sensible way of parsing, you mostly only need applicative, because monad is for that case where you have data dependency. You need to make a decision on which parser to run based on what you just parsed, right? In other words, your parsing is context sensitive. In other words, your parsing is inherently serial. You cannot parallelize that process if you have to make a decision based on what came before. You cannot easily parallelize it, perhaps I should say, because we're very ingenious. So that's parsing. Parsing is a very natural fit for applicative. Now, finally, I want to talk about asynchronous execution. In particular, senders and receivers. So there's a paper, P2300, which some of you may be aware of. It's proposing a particular asynchronous execution model for C++. It looks like it's going to make it for 26. And the authors of that paper, I'm pretty sure, are well versed in functional patterns, but they made a explicit decision not to mention any functional language in that paper. There is no mention of monad, there is no mention of functor, there is no mention of applicative. This is from Eric Niebler's really good pair of talks, where he shows a selection of sender adapters, right? Now, if we look at these and we know some functional language, we can see several of them are actually functional things. Then transforms the result value of an operation with a function. Well, that sounds like fmap to me. Let value, I'm saying nothing about the names in this paper, but it's called let value at the moment. Parses does the same thing as then, except that the function returns a new sender, right? The function returns a value in a contextualized value, a value inside the functor, if we like. That sounds like bind, right? When all takes a bunch of senders and completes when they all complete. That looks like a variadic fmap to me. That looks like what we saw with parsers, combining multiple parsers. In this case, combining multiple senders, and that's app, right? That's apply. So yeah, if we know some functional language, we can look at P2300 with new eyes and see, and you know, if like me, you're very used to thinking in terms of functional patterns, it can be very helpful to know that these things, that's what they really are, because then you know exactly what you can do with them. Yeah, so then is fmap, let value is bind, when all is some formulation of applicative. And as an icing on the cake, you know, just is pure, right? Just lifts a value into a sender. And this is how we know that P2300 is a sound design. It's not something that architecture astronauts have dreamed up with no experience. It has, indeed, it has multiple implementations now, and moreover, it's based on these solid functional patterns that we've known about for decades. So this is how we know it has the expressive power to solve problems of asynchronous nature. Now, more than any of the examples I've shown, I think it highlights how applicative is fundamentally parallel and monad is fundamentally serial, right? Because it's all about concurrent execution. So we're naturally thinking about, you know, is it parallel? Is it serial, right? So let value is monadic. It has a data dependency on its argument. It's for when you need a choice about which piece of work to kick off next based on what came out of the previous piece of work. When all waits on a bunch of senders and can clearly they're all could be running in parallel, right? And then when they're all done, that sender, the when all sender completes. And this is sort of obvious, the difference, right? When we think about it in terms of asynchronous execution, we could implement when all with let value, right? Every monad is an applicative. So what would that mean? It would mean running all the inputs serially and carrying the values they produce through monadically, which would sort of obviously be wrong because the whole point of this framework is to be potentially concurrent, right? If you serialize all these things that could run in parallel, that's obviously wrong. And so this really highlights the difference between applicative versus monad. Okay, that is about all I have time for. So just to summarize, we covered a bunch of instances of applicative in this talk. The simple ones you hear about are usually optional and possibly expected, but also ranges have, you know, those two formulations in zip and Cartesian product, and more generally we have parsing, we have continuations, aka sender receiver, and I didn't have time to cover some other stuff. So validation is very similar to parsing. And if you really get into sort of the functional side of things, then it turns out function application itself is an applicative functor. So, you know, I think we should, you know, we hear a lot about monad. I think we should hear a lot, even more about applicative, right? We shouldn't throw away monad because sometimes we need it, but there's this idea of you should only use the power that you need, right? Because if you can use something that's less powerful, it's also less constraining and frequently more useful. So yeah, if you've got an applicative functor, great. If you've also got a monad, better, right? If you only need an applicative functor, that's better than needing a monad, right? On the flip side. Yeah, so this is the sort of summary slide. So try to think of how functional programmers think, which is literally this high level architecture idea of like not how the functional patterns are implemented, but what they're for, right? So monads are for serial data dependencies. Applicative is less constrained and can be used for parallelism, right? And as we covered in the talk, you know, fmap, app, and bind or join are the characteristic functions of the three. And I think the way that applicative is often presented in the Haskell formulation limits thinking for C++. But thank you for listening. I'm at or over time, so I'll stop here and take any remaining questions that you have. Thank you very much.
Thank you. I have a quick question. So thanks for the talk. Very interesting. So a few couple of questions. One is when you talked about fmap 0, 1, 2, remember that? So
Yeah.
you talk about fmap 0 as a pure one. Is it the same as identity, or it's not related to identity
Let me try
function?
and find it.
It's
It's not the same as identity. Let me try and find.
yeah, this one.
That's a good slide, isn't it?
Yeah.
Yes. So identity would be A to A,
Right.
right? This is lifting. This is putting A inside the optional or inside the functor.
I see.
Right.
I see.
So
Got it.
pure for optional is just the optional constructor, right? And same for expected. But pure for and pure for a range would be ranges single, right? You're making a single range with the value inside it, or views single. I forget which one it is. And likewise, pure for a sender and receiver is called just. It's the sender that send when you do the work, it sends that value, right? So it's lifting the value unchanged into the functor.
Thank you. And you're using a lot of, so in the talk you're using a lot of Haskell. Obviously, you familiar with Haskell. I'm not. I didn't have an opportunity to do that. Do you think it's a prereq to better understand the domain?
Well, the reason I use I showed a lot of C++ as well, I hope, and I hope it was understandable, and I hope that you were able to sort of mentally map what you know through seeing the Haskell. I think Haskell is really useful for this kind of thing, particularly for doing type level programming, for just figuring out what the types are.
I see.
Because I would much rather read that than so that's what bind looks like in C++, and that's just a type signature, obviously. First of all, there's a lot of words on the page. Secondly, it doesn't really elucidate, functor of ... there. I sort of left out because it's hard to express that without 2-3 lines more of metaprogramming sort of thing.
Yeah.
Whereas in Haskell, you can just write that, and it's once you're used to reading type signatures, as I'm sure you can imagine, it's much easier to read a line like that than try to figure out what that's doing.
Yeah, I agree. Thanks. Okay, let's see if others have any question.
Mm-hmm.
Okay. No, nothing. If not, I'll let you go. Thanks a bunch, Ben. It was very interesting. Thanks. Yeah.
Thank you.
Thanks everyone. See you next time. Take care. Bye Ben. Take care.
Bye.
Bye.